What's up guys, my name is Rustagi and today I'm going to be teaching you everything you need to know about AP Physics 1 Unit 7, Rotational Motion. And this is pretty much the longest unit. But don't worry, my job is to simplify it for you. And if you haven't already, please go to the description right now and get my free AP Physics 1 book. Now that book has everything you need to know to get a 5 and an A in your class. So what are you waiting for? Get it immediately right now. And now, let's begin. Well, let's start with rotational kinematics. And rotational kinematics is pretty similar to kinematics from Unit 1. It's just that some of the variables are changing in the equation. For example, now we have angular velocity. And angular velocity in general is 2 pi r over time, or the period. And then we also have angular acceleration, we have time, we have angular displacement, which means like how much it displaces, like what angle it displaces by. So then please pause the video and observe all of these equations. Now, total acceleration. Now, total acceleration is basically when you have both radial and tangential acceleration. Now, this is different from uniform circular motion, because in uniform circular motion, we have simply only centripetal acceleration towards the center, and the velocity is constant, so there is no tangential acceleration, but sometimes there is, and in that case, the formula for acceleration is the square root of the centripetal acceleration squared plus the tangential acceleration squared. And this is very important because now this means that if there is a tangential acceleration, then the centripetal acceleration does not point towards the center. It's going to be pointing a little off from the center. And also, whenever in uniform circular motion, right, the angular velocity will have a relationship with linear velocity. V equals to omega r, where omega is the angular velocity times r, right? So don't forget your formula for centripetal acceleration. I'm going to be teaching you about another form for centripetal acceleration using our angular velocity. So basically, we know that in general our centripetal acceleration is v squared over r. And we also know that v equals to omega r. So if we substitute that in, we get omega squared over r. And one of the r's cancel out, so we're left with omega squared times r. And that's another form for centripetal acceleration. Now torque. So you can make an analogy regarding torque with force. Now torque is to rotation, as force is to linear motion. And then torque is basically, right, it's like the version of force, but in rotational motion. So basically it involves the force that we apply on an object and the lever or the moment arm, whatever you want to call it. I'm going to be calling it the lever arm. Now the component of force that is perpendicular to the lever arm, that's what can apply torque. And torque is known as the product of the force and the lever arm length. And the formula is the force times the radius times sine theta. And if you want to see some real life examples of torque, you need to check out my book. For example, a door, right? A door in your house, that's always using torque. And I'm gonna highlight all the concepts you need to know. So for example, if the force is as far as possible from the hinge, right, then the torque will be maximized, and that's why it's easier to open a door from the knob. For example, try pushing a door right near the hinge. It's not going to work because the lever arm, right, it's so small, right, it's so close to the hinge. But if we move that force all the way to the end, then it's going to be much easier to open the door, which is why the knob is placed on the opposite side of the hinge, not like right next to the hinge of the door. So please check out my book if you want to go deeper into torque. Now, rotational inertia is the rotational analog of mass, and it describes an object's resistance to changes in angular velocity. For a point mass, you simply use the formula I equals to mr squared, where r is that distance from the pivot. If you have multiple point masses, then you can simply find mr squared for each mass and then sum them all up. Let's see an example. So basically here the pivot point is that orange point, and then there's one ball 3 meters from it, and there's one 2 meters from it. And then the mass of the blue ball is 4, and the mass of the green ball is 3. So we know that the rotational inertia is mr squared, right? That's the formula we use, and we sum it up for both balls. So for the first one, it's going to be 4 for the mass times 3 squared. For the second one, it's going to be 3 times 2 squared. And we can sum this up to get 48 kilograms times meter squared. Now, this is one of the most important things. So we know by Newton's second law that net force equals to mass times acceleration. Now similarly, there's a Newton's second law for rotational motion. The net torque equals to the rotational inertia times angular inertia. Now there's also rotational inertia for extended bodies such as disks, hoops, cylinders. And for AP Physics 1, you don't need to memorize the rotational inertia formula for any of these objects, such as hoops or cylinders. But conceptually, you need to know why one has a larger rotational inertia than the other. For example, I'm going to be comparing a hoop and a disk for you. So on the left, I have a hoop, and on the right, I have a disk. A hoop only has masses at the ends, while a disk has it throughout the entire area. Now, what does this mean? Well, this means that the mass of a hoop, right, it's concentrated at the ends. So the mass is super far from the pivot, right? Let's say the pivot is at the center, right? It's super far from the center. And that means that the rotational inertia will be maximized, because if you consider like each small point mass for this whole figure, right, and you use the formula mr squared for it, r is always going to be large. But for the disk, there's going to be points near the center, there's going to be points close to the center, some a little more close, some less close, but there won't be as much mass concentrated near the circumference, right? Which is why the rotational inertia of a hoop is larger than a disk. So what is angular momentum? Well, I'm going to be showing examples. There's this circle, right? And it's moving with an angular velocity of 4 radians per second. And then the rotational inertia of this is 1/2 mr squared, where the mass is 2 kilograms and the radius is 4 kilograms. So now, in general, there's two formulas for angular momentum. One is mvr times sine theta. That's used for a point mass. And then there's one for an extended body, which is just the rotational inertia times omega. So basically, in this problem, we have an expression for I, the rotational inertia. So we have an expression for the angular velocity. Obviously, we should use L equals to I omega. So basically, the rotational inertia is 1/2 times 2 times 4 squared, which is 16. And we multiply that to omega, which is 4. And we get that the angular momentum is 64. Now let's learn about angular impulse, which is similar to the impulse we learned about when we were working with linear momentum. So basically, angular impulse is the change in angular momentum. And it's also equivalent to the torque times time. Now, angular momentum conservation. Now, when there is no external torque on a system, then the angular momentum is conserved. So basically, pause the video and please observe this formula. Now, I'm going to be showing you an example using a ballerina. So before I proceed with the example, I want to tell you that even if the distribution of mass is changing, angular momentum will be conserved. Pretend her arms are out initially and she's swinging, right? She's just rotating in circles. Now she pulls her arms in. What's going to happen now? Predict what will happen to her rotational inertia when she pulls her arms in. And how does this affect rotational inertia? Why does it affect it? Well, when the arms come in, right? All this mass in her arms, now it's concentrated near her axis of rotation. Because she's rotating around her axis, right? Now it's all concentrated around it, right? It's going to be super close to it. So that means the rotational inertia decreases because all that mass comes closer. And since we know that angular momentum is conserved and her rotational inertia decreases, the angular velocity must go up. Now I'm going to be showing you another example with using a rotational collision. So basically, there's a soccer ball with a mass m and it's kicked with a velocity v towards a rod. And then the rod has a mass lowercase m. And a rotational inertia of 1/3 mr squared when the pivot is at the end of the rod. And after collision, both the soccer ball and the rod rotate around the pivot together. What is the final angular velocity? So please pause the video and try the problem. Well, initially, right, so basically angular momentum is conserved in this problem. And the initial angular momentum would just be mvr because the soccer ball is like a point mass. And then this will equal to the sum of the rotational inertias of both the rod and the ball times the final angular velocity, because both of them rotate together. And then now we can divide both sides by IR plus IB, where IR is the rotational inertia of the rod and IB is the rotational inertia of the ball. So we now have an expression for our final angular velocity, and we plug in 1/3 mr squared for the rotational inertia of the rod, and we plug in mr squared for the rotational inertia of the ball because it's a distance r from that pivot. So now we can simplify this to find that the final angular velocity at which they both rotated at is 3mv over mr plus 3m times r. Now, I'm going to be teaching you about rolling without slipping. So whenever you're rolling without slipping, that means the linear velocity equals angular velocity times the radius. And static friction causes this. And in rolling without slipping, no work is done by static friction. And in general, whenever there's rolling without slipping, you need to account for both the angular velocity and the linear velocity, right? The velocity of the center of mass. So basically, the kinetic energy equals to 1/2 times the rotational inertia about the center of mass times the angular velocity plus 1/2 m times the velocity of the center of mass squared. So this is very important. You need to account for both rotational kinetic energy and the normal, like the translational kinetic energy. And the rotational kinetic energy in general is 1/2 I omega squared. Now let's look at an actual free response question from the actual AP exam. So please pause the video and try the problem on your own. So by now I hope that you actually pause the video to try the problem. So let's look at the solution. So this is from the 1983 AP Physics exam. So basically, there's a uniform solid cylinder of mass m1 and radius r, and it's mounted on a frictionless bearing, right? About a fixed axle through O. And then the moment of inertia of this cylinder about the axis is 1/2 m1 times r squared. And then a block of mass m2 is suspended by a cord and it's wrapped around the cylinder as shown above. And then it's released at time t equals to 0. So in part A, we want to identify the forces that act on the cylinder and on the block and draw free body diagrams for both. So let's think about the forces that act on the cylinder and the block. Well, for the block, of course there's going to be gravitational force downwards, and then there will be tension force upwards due to this cord. Now let's think about the forces on the cylinder. Well, there's obviously going to be gravitational force. Gravitational force will be downwards. And then there will be tension force to the right because the cord is tied to the cylinder also. Now there will be another force which we can denote as FH or something like that. And this force will occur due to the axle, and it's going to point upwards. Well, in part B, we want to find the acceleration of the block. So let's use Newton's second law. And we're going to combine this with Newton's second law of rotation. So let's use Newton's second law of rotation first. So we're going to be working with the cylinder first. So the only force that applies a torque on this cylinder is tension. And the torque is tension times radius. And this equals to the inertia, rotational inertia times angular acceleration. And the rotational inertia is 1/2 m1 times r squared. And then we can denote angular acceleration as alpha. And now we can use Newton's second law for the block to write the equation m2g, which is the gravitational force, minus tension equals to m2 times a, which is the acceleration. And then we use the Q relationship that the angular acceleration equals to acceleration divided by the radius. Now this is very important. So we can use this relationship and we plug this into our equation TR equals to 1/2 m1 r squared times alpha. And after we plug this in, we can simplify that equation to tension equals to 1/2 m1a. And now we can plug this into our equation for Newton's second law to get m2g minus 1/2 m1a equals to m2a. And now we can bring like terms to one side to solve for acceleration. And after we simplify, we get that the acceleration is 2m2g divided by m1 plus 2m2. And now in the second part for part B, we want to find the tension in the cord. We already found that tension equals to 1/2 m1a, and this was found by simplifying our equation that I just showed you. So we can simply use this equation and substitute our expression for acceleration that we just found, and doing so gives us 1/2 m1 times 2m2g divided by m1 plus 2m2, and this simplifies to m1 m2g divided by m1 plus 2m2, and that's the tension force. Now let's look at another free response question from the actual AP exam, so please pause the video and try the problem on your own before you proceed. Well, by now I hope you actually paused the video to try the problem, so let's look at the solution. So basically in this problem, right, we have two small disks of mass m and 2m, and then they're attached to a rod of negligible mass of length 3L. And then the rod is free to turn about a vertical axis through point B, and then these two disks, right, they're at rest on a rough surface, which means there's friction. And then the coefficient of friction between the disk and the surface is mu. And then at time t equals to 0, the rod has an initial counterclockwise angular velocity, omega naught, of about p. And then the system is gradually brought to rest by friction. Now in part A, we want to find the initial angular momentum of the system about the axis through point B. So we're going to use the formula that the angular momentum equals to I, which is a rotational inertia, times omega. And then we can find I, which is a rotational inertia, by considering the 2 point masses, the two disks. So they each have a mass, right? And then they're a certain distance away from the pivot, from this axis. So we get m1 times r1 squared plus m2 times r2 squared. And then the first mass is 2m and the second mass is m. And then the mass of 2m is L away from the axis, and then the mass of m is 2L away from the axis. So we can substitute the distances in to get 6ml squared. And then we multiply this to omega naught, which was the angular velocity, to get 6ml squared times omega naught, and that's the initial angular momentum. Now in part B, we want to find the frictional torque that acts on the system about the axis to point P. Well, now this is tricky, because there's going to be friction for both of the disks. Both friction forces will be leading to a clockwise torque. So let's find both friction forces. So we can find that the friction force on the mass 2m, right, which is the yellow mass that I just showed you, it can be found using the formula minus mu n, and that equals to minus mu times 2mg, because that's the normal force. And then for the other mass, of mass m, we can find that it's minus mu times mg, and we just get minus mu mg. That's the friction force on that. And now we can find the torque for this. So the first friction force, which is labeled in blue, that's a distance L away from the axis, and then the second one is a distance 2L away from the axis. So we multiply each force with its respective distance, and then we can find that the total torque is minus 4 mu mg L. Now we use the formula that the change in angular momentum is the angular impulse. So the change in angular momentum, so we know that the initial angular momentum is 6ml squared omega naught, and then the final angular momentum will be 0 because friction will cause the system to come to rest. And then this change in angular momentum will be equivalent to the torque times the time. So we know that the torque is minus 4 mu mgl, and then we know that the change in the angular momentum is minus 6ml squared omega naught. So we can divide both sides by minus 4 mu mgl. And doing so gives us that the time is 3L times omega naught divided by 2 mu g. Now thank you so much for watching this video, and please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams such as the AP exams. And also, don't forget to follow the Instagram if you have Instagram to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.